this lesson, we're going to start learning about trees. Trees are incredibly powerful and versatile data structures that are used commonly throughout computer science. In fact, many of the built-in data structures that you've used in Java before almost certainly have trees on their back end in their implementation side. So what we're going to do today is just look at why are trees valuable and why are they so common in computer science. Trees are widely used for their dynamic structure, meaning that things can be added and taken away from it very easily. A tree is an abstract data type that simulates the hierarchy you see in a real tree. There is a root value and subtrees of children with a parent node represented as a set of linked nodes. Trees naturally represent data in the real world. Take the example of a family tree where you have a parent whose children are below them in the tree, and then you've got the grandparents even further down the tree. Decision trees are also fairly common. Here is an example. If your house is clean, you might make a decision. Yes, my house is clean, so I just relax. No. Well, is my floor clean? Well, no, so I better sweep the floor. So these kinds of decision trees help guide decisions you might make. File systems are the perfect example of trees, where if I want to know that my path is users to Porter, I can trace the links between the nodes to see that in the tree structure. You can see that there's a root, then users, then Porter. Trees have a single root that they all originate from, a single parent for each node, and no cycles or loops. Here are some examples of valid tree structures. Here are the parts of a tree. You have a root node, which is the only one without parents. You have leaf nodes, which have no children. A node that branches off another node, or a parent, is called a child. Here are some key types of trees. There's heaps, binary search trees, and Huffman trees. If you make the structure such that root, the very top level, has to be the most important, you would use a heap tree. If you want to organize it based on character frequencies in, say, a body of text, then you would use a compression tree or Huffman tree. If you want to organize the data based on the natural ordering of the nodes, then you would use a search tree. With a generic tree, a parent can have any number of children, and a binary tree just restricts parents to having at most 2 children. So how would we construct this? The tree will have a linked list structure, meaning that it will be built by connections to different references. The tree itself only needs a root node, just like a linked list only needs a head. Then you need a reference to a node. But what do the nodes look like? There are 4 things that you'll need with a binary tree node. The first is the value. The second is the parent, or the node that your current node originated from. Then you need a left child and a right child. Keep these in mind as we will use these in our binary search tree method that is included with this lesson. Trees, the data is organized in some way. You're going to have the highest priority elements at the top of your tree, followed by elements in decreasing order of priority. So you would have to sort them essentially in terms of the ordering you want them to be in, for example, alphabetical. So if we were to search them, we would go by the order they are in. For example, if you have an array of these places, you want to find Chicago, you would do a binary search. First, you would find the middle element, which is England in this case, and compare the elements on either side to your key, which is Chicago. Lisbon comes after Chicago in the alphabet, so we disregard the second half of the array and focus on the first. Now, we find the middle of the first half of the array, which is Beijing. Agra comes before Chicago in the alphabet, so we look at the right side of Beijing. Chicago is the key itself, and so we have successfully performed a binary search. To search an array, you have to make sure that it is sorted first. This is not the case with binary search trees, so they are a better option for binary searches. In a binary search tree, the left subtree values are always less than the parent, so this would represent the left side of the array we looked at. Right subtree values are always greater than the parent, so this would represent the right side of that array. Using a binary search tree is beneficial because, along with being able to perform a more efficient binary search, you can remove and add items quickly as well. Now that we have a good idea of what a binary search tree is, let's talk about how we do a search in a binary search tree. The idea behind a binary search tree is very similar to binary search of an array. So first off, let's say I'm trying to find element C. Well, how am I going to get there? Well, I'm going to start with the root, and we'll look, and I'm going to say, is E C? Are those the same things? No, they are not. E is actually greater than C. And because E is greater than C, it tells me to disregard the right subtree and look at the left subtree of E. So my next step is to move my current notion of tree node down to B. I'm going to look at B and compare B to C. Are they the same? They're not. B is less than C. So I now need to look at the right subtree of B. And now I'm going to head and look at C. So in other words, in node C, we are going to ask, is C equal to C? It is, so we found it. We're done. All we have to do is return true or return the node depending on what we're doing with the search. We found this binary search tree contains the element C. So now that we have the idea of how to do this search, the question is, how are we going to put this into code? Well, first off, you could solve this fairly cleanly using recursion. And the way I want you to think about this is that if I'm thinking about what do I want to do at node E, the tree is rooted at node E. It's very similar to what I'm gonna want to do when I'm looking at the subtree rooted at node B, which is very similar to the comparisons I might make for the subtree rooted at C. So, because it's the same behavior at each step, this lends itself well to recursion. You can also solve this very cleanly using iteration. And here you would just have a loop where you essentially are keeping track of your current node. So just like we did before, you'd have your current node be E, then B, then C, and you can just essentially walk through the binary search tree this way. Thank you for watching, and you can check out the code attached to this video to understand more about trees.